Mark Blomquist here. I just wanted to do one more video, scientific video, going over what makes something turn. And a lot of people, when they think of an airfoil, they think of pressure difference and the speed or the velocity of the fluid over one side as opposed to the other. That's all valid, but there's another way of looking at it, and that is to look at the direction at which the fluid is leaving the transom or the rear edge of a foil or a boat or any object that's flowing through a fluid like a fish. So here I have a illustration of a canoe. This canoe has a rudder. The rudder is basically in line with the center of mass of the boat, and the boat goes straight and does not turn. Here is another canoe. This time the rudder is angled, and if you draw a line through if you split the tail end of the rudder, bisect the angle and draw a line through here, this is basically like a force vector, and this force vector is not going through the mass of the boat. So the boat will turn. So imagine if you had a propeller here and the propeller was pushing water backwards. It basically does the same thing. It's just that the rudder has no propulsion, but the boat is flowing in a fluid, so it acts like propulsion because it's redirecting the water flow. Instead of the water going that way, it's going this way. All right, so how does this pertain to, okay, so let's look at a non-cambered wing, basically, and a cambered foil. It's the same deal. With a non-cambered, if you bisect this angle, this one and that one, the line goes through the middle of the mass of the object and you get no rotation. So there are some airplanes that are designed this way. They're acrobatic airplanes and they have zero camber. And these are the airplanes that are designed to fly upside down and do all kinds of maneuvers. And then you also have cambered foils. And so the difference here is you have more curvature on the top and less on the bottom, and the fluid is leaving. If I draw a line and I split this angle, you'll notice that this projected line goes above the center of mass of this foil. So that is why an airplane has to have a tail. The tail actually directs fluid upward because the nose of an airplane would want to pitch downward. Now, the reason the tail doesn't negate all of the upward pressure developed by the wing is because of the size of the wing is much bigger, and the wing is always situated at the center of mass of the fuselage of the airplane, and the tail is always much further behind. So the amount of fluid or air that the tail has to direct upward to counteract the downward action of the front wing is very small. Okay, so now I've been experimenting with hydroplaning foils, and I started out with basically this shape, which is flat on the bottom but inclined, and it has an arc on the top. And so the water deflects, when it's on the surface, the water deflects at this. This is the direction of the water. It's 4 degrees downward. However, when this one goes underwater, if you bisect this angle, then the new projection is here. It's along this line. So what this does is it causes the foil to want to rotate and pitch downward if it is under the water. So with this foil shape, you have to have a really strong crossbar to prevent the nose from from wanting to curve under. Okay, so then I tried a wedge, and this was the last thing that my dad was working on when he passed away. He was working on a wedge shape. The wedge is basically very different when it goes underwater. So this is the flow in the direction of when it's on the surface, and when it gets submerged, the line basically goes right through the middle. And so you don't have any rotational effect. The wing does not want to rotate downward. And in this case, the wedge shape has a little bit more buoyancy. So you're relying mostly on buoyancy to bring the wing back out of the water. And then the third foil that I experimented with is this one. This is a stepped wedge. And the stepped wedge, this is the ideal angle, and then up here it gets a little bit steeper. So it's almost like a motorboat, like a speedboat. They all have a flat section and then they have a curved section. And so this is, when this goes underwater, this line goes through the center of mass and slightly below it. So with this foil, if this went underwater, it would want to go straight or slightly up. Okay, so then I tried this one. This one has slight arcs on the top and the bottom, so it's quite symmetrical. So when it's on the surface, the water is going at this angle, and then it's almost parallel. So if it does go underwater, there's almost no rotation on this one. It is a slight upward rotation because this line goes slightly below the center of mass of this foil. And here is another one, which I haven't built yet, I haven't tried yet. But this one is shaped more like it's almost like the bottom of a water ski. It's relatively flat, inclined, and then it curves. The center of curvature is here. And then on the top, the center of curvature is shoved backwards through here. And so if you take this and that and you bisect that, you get this line, and this goes above the center of mass of this foil. So this is another one. It looks like it would kind of go up if it was underwater, but this one would go down, same as this one. So these are very similar. This one would want to rotate downward, and so would this. So is this. So the one that seems the safest to me is the stepped wedge. If it does go underwater, it's not going to rotate downward, and it does have a lot of buoyancy, so it's going to want to rise because of its buoyancy. So anyway, that is the way I analyze. That's one way to analyze the shape of a foil and what it will do underwater. One more thing. Everybody's seen this experiment where you take a spoon and you put it in the water flow, and it rotates that way. So here's a spoon, here's the water. And as the spoon makes contact, what happens is the water flows around the spoon and goes this way, and the spoon moves that way. So everybody knows that. And that has to do with the fact that water is sticky and it sticks to the curve. And when it leaves, it leaves in the direction of the last, basically parallel to the last section of the curve. So that's why it leaves in this direction. And so that's why if the mass of the water is traveling now in this direction, the mass of the object, which is causing the disturbance in the flow, has to do the opposite. It has to move that way. So that's why anytime you see a curve in your mind, just draw an arrow perpendicular to the curve, and that's the direction that this surface will want to move. It's really simple. Okay, so what if you took a spoon and then you put a little flat section here here, let me redraw this. What if you had a shape like this and then you went like that? Would this spoon go that way? The answer is no, it wouldn't. The flow starts here and the flow leaves here. So this shape is neutral. It does not matter what this curve is, it matters what the curve is at the trailing edge. So anyway, that is why I chose the reflex stern on all of my boats, because what it does is it prevents your boat from being sucked downward into the water, and it creates a pitch neutral ride through the water. So the bow doesn't pitch up or down, it just goes straight. And anyway, and that's kind of what you want with a boat that has hydroplaning wings or discs attached to it. You want the main hull to be pitch neutral, so that the wings or the discs basically maintain the same or the correct or the ideal angle of attack with respect to the surface of the water.